To understand quantum mechanics, physicists start with the hydrogen atom. It serves as the baseline for the entire field. With a single electron orbiting a single nucleus, the math is exact. The equations yield perfect calculations for the electron's energy and position. But hydrogen is an isolated case. Almost all matter contains multiple electrons. To find the next simplest system, we look at helium, which has exactly 2 electrons. Adding that single extra electron breaks our ability to calculate an exact solution. The math used for hydrogen no longer applies. To describe atoms, chemistry, and solid materials, we have to deal with multiple interacting particles. We have to confront the many-particle problem. This equation shows the Hamiltonian, the total energy, for hydrogen, calculating the electron's kinetic energy and attraction to the nucleus. For helium, the equation expands. But the math becomes unsolvable at this final addition, the electron-electron repulsion term. Because both electrons have a negative charge, they repel each other. You cannot solve for the path of electron 1 without already knowing the exact location of electron 2. Their motions are inextricably linked, a state known as electron correlation. Since the particles interact and repel, the system must be governed by a specific set of rules regarding how identical quantum objects coexist. In classical physics, macroscopic objects are distinguishable. If a red and blue ball swap places, you can still identify them. But quantum particles operate under strict indistinguishability. Identical electrons share the exact same properties. If swapped, their measurable probability must remain perfectly identical. There are 2 possible mathematical solutions to this requirement. When particles exchange places, the wave function yields a positive, symmetric output, or a negative, antisymmetric output. Electrons are fermions, requiring their wave functions to be antisymmetric. When 2 electrons swap, the math demands a minus sign. This single negative sign serves as the hidden architecture dividing all matter in the universe. Imagine 2 identical fermions occupying the exact same state, phi. Multiplying their states yields an inherently symmetric result, but fermions require an antisymmetric state. This creates a direct logical conflict. The only number equal to its own negative is 0. The probability of 2 identical fermions sharing the same state is 0. This proves the Pauli Exclusion Principle from first principles. An electron's wave function combines space and spin into an antisymmetric total. A singlet state's antisymmetric spin forces a symmetric spatial part, moving electrons closer, raising repulsion. A triplet state's symmetric spin forces an antisymmetric spatial part, separating them and lowering energy. These required symmetries dictate how close electrons can physically get to one another, directly altering their electrical repulsion. This exchange interaction is not a classical force, but a purely quantum effect that drives chemical bonding and magnetism. Bosons, which don't follow this rule, can collapse into the exact same ground state and cluster in the same space. Because electrons are fermions, they must fill distinct, separate quantum states, building structured atomic shells rather than collapsing. This forced separation creates physical atomic volume and determines the electronic configurations that make elements reactive or stable. The Pauli Exclusion Principle resisting compression is what gives solid matter its rigidity and strength. The reason you cannot walk through walls is the mathematical requirement of fermion antisymmetry. These rules scale to the cosmos. When a massive star runs out of fuel, it collapses under its own gravity. As the star crushes inward, electrons are forced closer together until they run out of available distinct quantum states. This triggers electron degeneracy pressure. The fermions reject sharing states, creating an outward pressure that halts the star's collapse. This traces back to the foundational rule of the universe, the equation for identical fermions. From the energy levels of helium to the stability of dead stars, physical matter is defined by that single negative sign.